Hello, my name is Colton Gerber. I did my research with SUNY Binghamton. My presentation is on how batteries made with calcium instead of lithium could be better for electric cars or storing renewable energy. This in the bottom left is a summary of my main results. I'll make sure to get to that at the end. For now though, why do we need these batteries? Well, by 2030, batteries may provide between 9 and 38 times more energy to the grid than they do now. Here's a conservative estimate for 2030. Here's a maybe the maximum estimate for 2030. The materials we use for these batteries, calcium and magnesium, are more abundant than lithium, and this is a times 10 for each tick on this axis. So calcium is about 1,000 times more abundant than lithium. Magnesium is about 100 times more, and even more important than that is cobalt, which is used in a lot of lithium batteries, and it is even less available than lithium. And why is that an issue? Well, demand for cobalt for lithium batteries is expected to outpace supply. And this has happened before. We've seen that more of these exploitative mines open up. Most cobalt does come from the Democratic Republic of the Congo, and 10 to 30% of that comes from mines, exploitative labor practices. And greater demand only incentivizes more exploitative mines. So we need an alternative to using cobalt. A little bit more on batteries. Batteries usually charge and discharge by a process called intercalation, where ions, say these light ones, move in between the host atoms, these darker ones. So they kind of slip in between these layers. Or in the case of spinel, the material I'm studying, there's these channels. You can see not from this direction, but from this direction, there are these big channels. And they might even be big enough to allow ions like calcium through, and not just lithium. The methods I used fall under an array of methods called DFT, or density functional theory. That's just referring to, well, I guess wave function densities in quantum mechanics, but it's a computer modeling system. It takes structures and tries to find lowest energy, like most stable structures. So those are the structures we're likely to see happen. And this is a representation of how that works in a basic way. So this is kind of a ball rolling down a hill, right? So if I have a structure up here at C, I kind of go off to the left here, I'll end up here down at A. And so my simulation might relax down into this A state. However, it could also mistakenly go over towards B and get stuck here, so that can cause some issues. I made voltage profiles for spinel cathodes, and that shows the voltage produced as the structure goes from empty to full. And so how that goes is as these ions fill in, you can see this voltage profile going across and filling in as well. And we're almost to full, and there we are. So this is what the voltage profile graph looks like. The energy between structures is used to calculate the voltage. A little finer detail about that. So you'll notice that there's only a few steps in here. Despite having 8 ions go in, I only have, I guess, 3 different states. And that's because I don't actually go 1, 2, 3, 4, 5, 6, 7, 8. I might skip from 0 to 4. And that's because these other states aren't as stable. So I'll go straight from 0 to 4, then to 7, then to 8. And that won't happen throughout the entire structure because you'd have to completely charge or completely discharge it all in one step. And that won't happen, of course. So regions will go from 0 to 4. And then once it's all at 4, some regions will go from 4 to 7 until it's all at 7. And then the last one will fill in. So here we're getting to my final results. So we have calcium, magnesium, and zinc. And I have voltage profiles for all of these. You can see they're slightly different. Magnesium actually ends up being lower on average than calcium because of these lower steps over here, and zinc is just too low. So all of these have weight and size similar to lithium. So that's what this graph over here is saying. Storage by weight, or gravimetric capacity, storage by size, or volumetric capacity. Calcium in blue, magnesium in orange are similar to lithium in green here. And these are all normalized to lithium's values. That's why it's percent and not actual values. The average voltage though, calcium and magnesium are lower than lithium. You can see that they're only about 60%. However, the hope is with 20 or 30 years of development on lithium, that same 20 or 30 years of development applied to calcium and magnesium, they could very well reach where lithium is now. And again, the supply for calcium and magnesium is just so much larger than that for cobalt, lithium and cobalt required for lithium batteries. That's my presentation. Thank you for watching. Again, my name is Colton Gerber. I did research at SUNY Binghamton with my co-authors Michael Woodcock and Manuel Smoo under the NSF RU grant. Thanks for watching.